One of the most tedious parts of running a faceless YouTube channel is the actual video assembly. I found myself repeatedly merging images, synchronizing audio, and adding simple captions. My previous workflow involved dragging elements into a consumer-grade video editor, which was slow and error-prone, especially when I needed to make global changes or scale up to many videos. I needed a programmatic solution that could take a collection of images, an audio track, and a simple text file for captions, then output a complete, polished video. The goal was to eliminate manual editing entirely for this specific type of content, a slideshow-style video with a voiceover. This wasn't about complex transitions or motion graphics, but rather reliable, repeatable production. I was specifically looking to incorporate a Ken Burns-style zoom and pan effect on each image to add some visual dynamism, rather than just static slides. And of course, hard-coded captions were a non-negotiable requirement for accessibility and engagement. This meant deep diving into FFmpeg, a tool I'd used before for basic conversions but never for a full assembly pipeline. My first challenge was orchestrating FFmpeg from Python. The subprocess module is the standard for this, but building complex FFmpeg commands can quickly become unwieldy with plain string concatenation. I explored a few Python wrappers like FFmpeg Python, but for the precise control I needed over filter graphs and dynamic expressions, I found it more reliable to construct the raw FFmpeg commands myself. This allowed me to debug directly with FFmpeg's verbose output, which is invaluable when dealing with video filters. The core idea was to generate a series of FFmpeg commands, one for each image segment, then concatenate them. Each image segment would have its own Ken Burns effect and duration, precisely matched to corresponding audio chunks. This modular approach meant I could easily swap out image sets or audio without re-rendering the entire video from scratch, which was a significant improvement over my prior manual process. I decided on a clear input structure, a directory of images, a main audio file, and a JSON file containing caption data with timestamps. The Ken Burns effect was the most complex part. FFmpeg's zoom pan filter is incredibly powerful but requires careful calculation. For each image, I needed to define a start and end zoom level, and a start and end pan position. These values had to be interpolated smoothly over the duration of the image's display. I wrote a Python function, generate Ken Burns filter, that took an image index, its duration, and some randomized parameters like initial zoom and target zoom range to generate the zoom pan filter string. The X and Y coordinates for panning also had to be calculated relative to the image's dimensions to prevent cropping out important parts. I found that starting with a slight zoom, for example zoom equals 1.05, and slowly zooming out or in zoom equals min zoom plus 0.00051.1 while simultaneously panning X equals ew/2ew/zoom/2 created a natural, subtle movement that kept the viewer engaged without being distracting. This dynamic filter expression was crucial for avoiding a static look. After generating the Ken Burns filter for each image, I needed to combine them. FFmpeg's concat demuxer is perfect for this, but it requires each input segment to be a standalone video. So, the pipeline first generates individual video clips for each image, complete with its unique Ken Burns effect, using a command like FFmpeg loop1i image.jpg vf zoompan equals t duration output clip.mp4. Once all clips were generated, I created a text file listing these clips, one per line. Then, a final FFmpeg command FFmpeg fconcat safe 0i clips.txt copy final video no udio.mp4 efficiently concatenated them, without re-encoding, saving significant time. This two-stage approach, individual processing followed by concatenation, was far more robust than attempting to build one massive FFmpeg command for the entire video, which often hit command line length limits or became unmanageable to debug. Adding captions involved another FFmpeg filter, subtitles. I had my captions in a JSON file, like text, hello, world, start, 0.5, end, 2.0. To use FFmpeg's subtitles filter, these needed to be converted into a standard format, typically SRT or AS. I chose AS Advanced Substation Alpha because it offers more styling options, like font, size, color, and background box, which I wanted for a professional look. I wrote a Python script, create captions, to convert my JSON data into an AS file, carefully calculating line breaks and timing. The FFmpeg command then became FFmpeg I video on captions.mp4 vf subtitles equals captions.as::force style equals font name equals Arial font size equals 24 primary color equals and H00. FFFFFF outline color equals and H00000000 back color equals and H80 million border style equals 1 output with captions. .mp4. This hard burns the captions directly into the video frames, ensuring compatibility across all platforms, including YouTube's embedded player where soft subtitles can sometimes be problematic. The final step was combining the video track with Ken Burns effects and captions with the audio narration. This is a straightforward FFmpeg map operation. I had final video with captions.mp4 and narration.mp3. The command was FFmpeg I final video with captions.mp4 I narration.mp3 C:\v copy C:\AOC map 0:v:0 map 1:0 final output.mp4. I specifically used C:\v copy to avoid re-encoding the video stream, preserving quality and speeding up the process significantly. The audio was re-encoded to AAC for broad compatibility. I also ensured that the audio was precisely aligned with the video duration. If the audio was shorter than the video, I'd loop the audio or pad the video. If the audio was longer, I'd trim it. For this project, I made sure the audio was the exact target duration, often by generating it from 11 labs with a precise duration limit, avoiding any length mismatches entirely. I wrapped this entire process into a Python class called Video Assembler. It exposes a public method, assemble video image dir, audio file, caption sound file, output path, which encapsulates all the FFmpeg calls and temporary file management. Internally, it manages temporary files for individual video clips, the concatenated list, and the AsCaption file. I used tempfile.name temporary file for this, ensuring that these intermediate files are automatically cleaned up after the video is assembled, which is crucial for preventing disk bloat during large-scale operations. Error handling is also critical. Each subprocess.run call checks its return code and stdir to catch any FFmpeg errors and log them appropriately, preventing silent failures. This robust class now forms a core component of my broader YouTube automation pipeline, allowing me to generate an entire video with a single function call, abstracting away all the underlying FFmpeg complexity. This entire system has significantly streamlined my content production. What used to take 30-60 minutes of manual editing for a 10-minute video now takes about 2-3 minutes of compute time on a modest server, not including the time to generate images and audio, which are handled by other parts of the pipeline. The cost for this FFmpeg processing is negligible. It runs on a small AWS EC2 instance that costs me around $5 a month, shared with other automation tasks. The most valuable aspect is the consistency and scalability. Every video generated follows the exact same visual and captioning style, and I can queue up dozens of videos for production without any human intervention. This setup frees me up to focus on script writing and research, rather than repetitive video editing. If you're building out similar automation pipelines and want to avoid the manual grind, dropping a star on the GitHub repo for this project, which I'll link below once I clean it up for public release, would be a great way to support the channel. I'm also planning a follow-up video on integrating this with a Claude API-driven script generator, so subscribe to catch that when it drops.